In this video, we are going to talk about the remainder theorem. Now, this theorem you're going to use more in the next math class. So in this video, I'm going to discuss what the remainder theorem is, but please know that we're not going to use it a whole lot in this class, but you will next semester. So the polynomial theorem pretty much says that if I want to know what the value of this function is when I plug in, let's say, whatever number I give you, so in this case 2, that the answer you would get by plugging in 2 is the answer you would get if you use long or synthetic division. So let me show you what I mean. So previously, whenever I gave you a problem that looked like this, you would know that this means to plug this number in the x spot into the problem. So I'm going to go ahead and take out the x here and plug in a 2 and plug in a 2 here for x. And then I would use my order of operations, so exponents first, so 2 squared is 4. And then after exponents, an order of operations is multiplication, here and here. And then 20 minus 14 is 6, plus 3 is 9. Okay, so we would get the answer 9. Now what the remainder theorem is saying is that I could take this 2 here and I could use division. So I can use long division or synthetic division. So I'm going to go ahead and use synthetic division. So I could take the 5, the negative 7, and the 3, and I'm going to put a 0 here. And then I'm going to add, multiply, add, multiply, add. And that was way quicker, especially if the problem was really nasty and had a lot of exponents and I didn't have a calculator. This is way quicker. So this is what the remainder theorem says. You get the same answer by using division. So if a problem was given to you like this, yes, you already know how to do it. Plug in a 2 for all the x's. But if it says use the remainder theorem and you do it this way, you'll get the right answer, but it just means you'll lose points if it says use the remainder theorem. Now on your homework, I don't grade your work and stuff like that when you're doing your online homework. But on a test, if it says use the remainder theorem, then this is what I'm wanting to see. Now you could also use long division instead. So let's discuss how we would do that if we want to do long division. So with long division, we take the whole entire polynomial. So 5x squared minus 7x plus 3. And then what goes out here, so we have to think backwards. So in order to put 2 here, we had to have had x minus 2. Because remember, the number that goes out here is what you get when you set the denominator equal to 0. So then if we added 2 to both sides, we would get x equals 2. So that is how I know that there should be an x minus 2 out here. Because with long division, this is where all the x's are there. So this 2 right here, I'd have to go backwards. It came from x minus 2 equals 0. So that's how I know to put an x minus 2. Okay, then with long division, I would put a 5x up here because 5x times x makes 5x squared. And then 5x times negative 2 is negative 10x. And then we subtract. So 5 minus 5, that's 0. And then over here, this is negative 7 minus negative 10. And that makes 3x. Then we bring down the 3. And then x times 3 is 3x. And then 3 times negative 2 is negative 6. And then we subtract. 3 minus 3, that's 0. And then we have 3 minus negative 6 is 9. And then the remainder is the answer we got here. So the remainder here is 9, which is what we got here, which is what we get when we plug in 2. Now, I ran out of room on your notes page, so I actually want to do one more problem. So if you would either grab another sheet of paper, or if you have room on your paper, let's go ahead and do one more problem. Okay, so let's recap. The remainder theorem says that if we divide using synthetic or long division, that the remainder would be the answer to the given x value. So in other words, this is the old way, and it's not wrong. It just doesn't use the remainder theorem, which is what we're trying to practice right now. So the old way is when we see f of negative 5, and again, this only works if the function is a polynomial. I can plug in a negative 5 for all the x's. But this actually, if you didn't have a calculator, if I were to race any of you and you did it this way and I used the remainder theorem way, I would probably beat you because it actually is a lot more efficient when there are higher exponents. So imagine if you didn't have a calculator. You'd have to do negative 5 times negative 5 times negative 5 times negative 5, right? I'm not going to do that because for time's sake. So negative 5 raised to the 4th power. It's not an issue for us. We have a calculator, but I like to always make decisions in math as what would be the easiest way if I didn't have a calculator. Okay, so then I have more exponents here. So negative 5 raised to the 3rd power. It's negative 125. So imagine again, this is what you should be thinking about. Oh man, if I didn't have a calculator, this would not be fun. And then after exponents is multiplication. So I'm going to multiply all of these here. So I'd have 3 times 625. Again, imagine if you didn't have a calculator, having to multiply and get 1,875. And then imagine doing negative 125 times 2. So negative 250. And then negative 5 times 25. And then without a calculator, if you didn't have one, having to combine all of these. Luckily, we have a calculator, right? It's not an issue. And we would get 1,481. So again, that's the way we were taught. This is the way we would do any problem. So for example, let's say the problem looked like this. If I asked you to find f of, let's say 5, you'd plug in a 5 here and a 5 here, and you would get 8/7 for your answer. So the remainder theorem will not work on this problem because this is not a polynomial. This is a rational expression. So because this is a polynomial, a bunch of terms being added and subtracted where their exponents are all positive, instead of doing it this way, which takes a lot longer, because this is a polynomial, instead I could take the negative 5 and I can take all the coefficients, so the 3, and then the 2, the negative 5, the 4, and then the 1. And then I'm going to put a 0 here, and then add, multiply, add, so 2 plus negative 15. Then I'm going to multiply here, so negative 5. If I didn't have a calculator, this wouldn't be that bad. So 65. And then I would add, then I multiply, then I add here, so 4 plus negative 300. Oops, too many zeros. So it's negative 296. Then I multiply here, so negative 296 times negative 5. That's 1,480. And then I add, and I get 1,481, which is the same thing we got up here, but this took a lot longer to have to do all those exponents and then multiply and so on. And we got the same answer. So this is what the remainder theorem says. If you use synthetic or long division, the remainder is the same answer we would get from plugging in the number. So for time's sake, I'm not going to use long division, but just to discuss the setup, if we were going to use long division here, the inside here would have the 3x to the fourth plus 2x cubed minus 5x squared plus 4x plus 1. And then out here, if it's a negative 5, it had to be x plus 5. So that way when we set it equal to 0, that's how we would get the negative 5, by subtracting 5. So then there would be an x plus 5 out here. And then you would just do long division and get the remainder, which would be this number here. So again, this is synthetic. It doesn't use all the variable parts, whereas long division does. So we have to go backwards and think about what would we set equal to 0 to get that negative 5. So if we take a look at this next one, if f of x equals 6x plus 4, so you could either continue writing this down where you did the other one, but like a problem like this one, it would be much more efficient to just plug in the 2 for the x and get 16. But again, I just want to make sure, even though this one's a much simpler problem, that if I take the 2 and I use synthetic division where I take the 6 and the 4 and I put a 0 here and I add and then we multiply, the remainder is again the same answer. So this is a problem where maybe I wouldn't use the remainder theorem. It'd be much more efficient to just plug in the 2 for the x. But again, I want you to see that they match here. Okay, so since this is a 2 here, if I go backwards, it would have been x minus 2 to get that 2 as the solution. So if I did x minus 2 on the outside and then the 6x plus 4, 6... Okay, 6 times x is 6x. And then 6 minus 6 is 0. And then 4 minus negative 12 is 16. So again, the remainder is the same answer if I had just plugged in the 2 for the x in this problem. So that is again what the remainder theorem says, that you could use long division and synthetic division and find the remainder, and it would be the same thing as if you have plugged in that given number here in for all of the x's. But again, I would never do the remainder theorem on this problem, but on the previous 2 problems we did, I would. Okay, so I want to add one more problem, and now this problem is going to show you how this relates to how you're going to use this concept in Math 150. So this is just a little bit to get us ahead. You don't need to know what I'm about to explain here, but I want to make a connection so that you can see how you'll use this in Math 150 or in the next math class. So what you do need to know is that, yes, I could plug in a -2 for all the x's, but I could also use the remainder theorem, and I take the coefficients if I use the synthetic division. So it goes 3 is the highest exponent, 2, 1, and then nothing. So I got to put a 0 there. So it always has to go 3, 2, 1, the constant. So then I add 0, multiply, add, multiply, add, multiply, add. So the remainder here is 0. Okay, let's do this one. So -3, and then I put my numbers here, and then put a 0, and then I add, multiply, add, multiply, add, multiply, add. So I get a remainder here of 0. Okay, let's try the next one. So I add, multiply, add, multiply, add, multiply, add. And the answer here would be 280. So this one would be, the answer is 0. This one was 0. And this one was 280. So now what I'm going to do next is I'm going to go ahead and graph this. Now I want you to keep in mind that both of these came out to be a remainder of 0 in the end. So that means if I plug in -2 for all the x's, it comes out to be 0. Same thing with -3. But when I plug in a 5 for the x, I get 280. Now keep that in mind. -2 and -3 both came out to be 0. So now I'm going to go graph this, and I want to make a connection for you. So if we take a look at the graph of this, remember we got a 0 when we plugged in -2. And so here's -2 right here. And you could see it's on the x-axis. The other answer we got that had an output of 0 was -3, and that's also on the x-axis. But the other number, which was 5, and if we look at the graph over here, if I go to 5, it's like right here, there's no point on the x-axis. We got 280. So the connection that I'm trying to make is, for your next math class, you're going to use the remainder theorem to help you find where the graph crosses the x-axis, because you will need that for something in your next math class. So again, you'll use synthetic or long division to find what numbers will get you a remainder of 0, because that will tell you where the graph crosses the x-axis, your zeros or your x-intercept, x values.